So one of the interesting applications of the ideal gas law is calculating the molar mass of a gas. And it goes back to the idea of what are units of molar mass. And when you look at molar mass, what you find, right, is that its units are grams per mole. So let me explain to you how this is done in the laboratory. And this is the experiment for the first part of this week. We actually take a liquid and stick it inside an Erlenmeyer flask. Now, an Erlenmeyer flask looks like this. I'm not a very good artist, but it looks something, doesn't look like anything like that. There, let's just make a bottle out of it like that. That's my Erlenmeyer flask. And then what we do is we put a volatile liquid in here, okay? So, and it's usually about 5 mils, like this. And then I put a lid on here. And that lid is made out of foil. And then I put a little hole in it, so a little tiny hole in the top. And I do that with a pipette usually, or a syringe, or a pencil, like a very sharp pencil. And then what you do is you heat this in water, like this. Now there's no water on the inside of the flask, but the temperature of the water is hot enough that it will cause the liquid on the inside to boil. Now, as it does that, what it does is it fills this whole inside of this container. So over time, what it looks like is it looks like the bottle, oh, this is going to be a better shaped bottle already, I can tell, is empty. It'll have a little hole in the top, but this is filled with the gas of the volatile liquid. Volatile liquid just means it boils at a low temperature. So basically, it boils at a temperature lower than water. We stick it inside the water. It boils. When it boils, it turns to the gas state, right? And it displaces any of the air that's in here. So this is heated, right? And then we cool it. And what happens is the gas recondenses. And so you have a little bit of liquid in here. That liquid, and the lid's still on here, that liquid is the liquid that was created by the condensing gas. So what information do we get from this, right? Well, we can weigh this, right? And we know the volume because it's a flask. We can fill it with liquid and we can measure its volume. And we know the temperature of the water. And so we'll measure that. And the other thing we'll know is we'll know the atmospheric pressure, like this. So this is my total pressure. And that's a really high atmospheric pressure. But this is the how you would get the data. So I get the liquid, I get the mass of the gas. It's this number. I get its volume, which comes from the flask. I have the temperature, which comes from the water, and then I have the atmospheric pressure. Okay. Now, at this point, I actually did this problem, and then I realized I wanted to talk about something else, and I stopped, and I'm redoing the problem. So I'll put it like this. You have everything you need now to calculate the molar mass of the gas because you have the grams from this and all this other information, the liters, the temperature, and the pressure allow you to calculate moles. So for example, I know PV equals nRT. I'll use ideal gas law. I'm just going to use PV NNT. Pressure is 975 millimeters of mercury. My volume is 0.279. And liters, and the temperature is 88 degrees Celsius. And my moles, well, that's what I'm looking for, because that's what I'm going to use here, okay? In fact, let's just do this. That's what I'm finding there. And then this number, right, that's my grams. right there. So once I have those two values, I can calculate the molar mass. So I'm going to make a little section over here. Oh, actually, I can't do it right there. I'll do it right here. I know PV equals nRT. And I can solve that for n. So n is equal to PV over RT. Now all I need is to convert the values over so I can plug it in. Now remember, R is, I'll write it up here, 0.0821, but the units are what's important. Liters times atmospheres divided by moles times Kelvin. You notice this is in atmospheres, but this is millimeters of mercury, so I need to convert that over. There's 760 millimeters of mercury in 1 atmosphere. The volume's fine. The temperature needs to be in Kelvin, 273. I have to add that. So that's going to be 361 Kelvin, like that. So this pressure, when I calculate it, pull my calculator here, is going to be, let's see, 975 divided by 760. That'll come out to 1.283 with 3 sig figs ATMs. So now I can plug it in. I can say N is equal to pressure, 1.283 atmospheres, times volume, which will be 0.279 liters, divided by R and T, that's 0.08221 liters times atmospheres over moles times Kelvin, and then my temperature is 361 Kelvin. Now, when you do this, you're going to get a tiny number, so let me pull that up. You do the calculation, 1.283 times 0.279 divided by 0.0821 divided by 361. That ends up being 0.01208. Ooh, 0.8. I just ran out, and that's moles like that. Just running out of space here. Now, to get the molar mass, I'm going to do this conversion without showing you how to do it, but it's 0.827 grams. It's a milligram to gram conversion. Divided by 0.01208 moles. And that's going to be 0.827 divided by 0.01208. Yeah. 68.46. Now I think I did this before I came up with a different number, but it's very close. I think I did a little calculation error somewhere, either this time or the time before. But that's how you calculate. That's the molar mass of that gas. Okay, but it took a lot of space because I showed you the setup. If you were just given the numbers, then you wouldn't have to write like all this stuff like I was writing here. But you'll be doing the experiment this week or watching the video for the experiment. So those are the numbers you'll pay attention to. You'll pay attention to how much the flask weighed before and after the liquid condensed in it, right? That'll give you your mass of liquid. You'll pay attention to the temperature of the water, and then you'll pay attention to the volume of the flask. And then I'll tell you, like, the pressure is 975 millimeters of mercury, right, for this one, but it'll be probably closer to 1 atmosphere in the video. I don't remember exactly what it is, but it's pretty close to 1 atmosphere. All right, so that's how you solve, again, for the first lab this week, how you solve for the molar mass of a gas.